Hello, everyone. Welcome to MCLA and tonight's first presentation in this semester's Green Living Seminar. I'm Elena Traster from the Environmental Studies Department here. So this semester's Green Living Seminar is organized around the theme of environmental pollution. All presentations are free and open to the public. They take place on Thursdays at 5:30 here in the Feigenbaum Center for Science and Innovation, room 121. I think this presentation today will last about 45 minutes with an opportunity to ask questions at the end. And a quick announcement for next week's presentation on Thursday, February 6th, Paul Godfrey, Emeritus Director of the UMass Amherst Water Resources Research Center, will present a lecture titled Acid Rain, How Research and Volunteerism Contributed to Addressing an Environmental Challenge. If you would like announcements about upcoming presentations, there is an email sign-up list right at the end of the first table down here, so you can add your email to that list, and you will hear from me. Also, if you stick around after the talk, there should be pizza outside. You're welcome to help yourself. Today's presentation on plastics in the environment, separating myth from reality, will be given by Dr. Chris REDDY, Senior Scientist at the Woods Hole Oceanographic Institution, and we are so glad to have him here with us tonight. Thank you so much.
When I was asked to give a talk here, I have a long history. I was here in 1990 for one night at a bowling alley, actually in Williams, but I remember going to North Adams, and I remember befriending a few students here. And I actually have another connection at North Adams that I'll talk about in your college at the end of my talk. And so it's important for me to be here. I'm going to talk about plastics today and the environment. It's entirely likely that you're going to be very angry at me. And if you do, that means I did a good job in some respects, because you are giving me 45 minutes of your precious time, when the typical attention span for folks when they read email or look at the web and even Twitter is about 4 seconds. So you're being incredibly generous to me, and because of that, that means I have to deliver. And if I don't deliver, then I had a missed opportunity. So my goal is for you to leave and talk about me afterwards. Not, the guy spoke funny with a really bad Rhode Island accent, but, I didn't know that, right? I'm successful if you talk about that with your dorm mates or your friends or your parents or the professors tomorrow or any other way. If I've touched upon you longer than 2 minutes and you're eating the pizza, then I won. And you won. We all won, I think. So, anyways, that's my goal. And, we might as well get started. Do we have advance? Yeah. Okay. So I have a bunch of colleagues that work with me. Colin Ward is another professor with me. The other three women are all students. Cassie and Julia were undergraduates who were doing research in our lab, and Anna is now a graduate student with Colin and I. But the lion's share of the work that's gone into this paper and that was ultimately published was on the efforts of two undergraduate research students. And I want to underscore to you the importance and the capacity and what you can deliver as an undergraduate and research. Don't ever sell yourself short, because they didn't, and they really delivered for us. So we're both in Massachusetts. I just so happen to be, I think, as far away as possible from you folks right now. And I'm at Woods Hole Oceanographic Institution. We have about 1,000 scientists and other folks. We're the largest marine science research institution in the world that's nonprofit and non-governmental. It's nonprofit and non-governmental, and it's about as good of a life as you can have. And I've been there about 23 years, and I live somewhere maybe around over here, and so it's a very nice life, and I don't even have a car because I can ride my bike to work every day. And so it doesn't get any better. You're successful in your life and your career when you get excited to go to work every day, and you suddenly look at the clock and you say, I got to get home. And that's what you want to strive for. Don't worry about money. It's easy to say that, but do something you love, and you'll be much happier. So throughout my career, I've studied pollution. Whether it's the soot that goes out of cars or oil spills or even compounds that are kind of natural pesticides in the environment, did my PhD on what happens when you build roads with recycled automobile tires, which is now coming back. I've looked at how you can make nanotubes and nanoparticles for different materials, and you can synthesize them in a way that has the least impact to the environment. And on and off for about the last 12 years, I've studied plastics. For all these products, I've never really worried. I'm going to say this without sounding like a jerk. I only care about these chemicals and as an opportunity to see how nature responds to an uninvited guest. So I'm curious about when humans release car tires or soot or a pesticide like DDT, or you're going to hear about PCBs in a couple weeks. How does nature respond? How does nature push back? Does nature win? Does nature lose? When does nature win? When does nature lose? It's a fantastic struggle. It's a great opportunity for us to understand how nature works. And often we can take that knowledge that we've gained and help bring that into how we design future chemicals or how we go about cleanup in other areas. And in this case, talking about plastics, a lot of the research that we're doing is trying to communicate and work with industry and other groups about how we can make the next generation plastics in a way that will have the least amount of impact. So that's our overarching goal for a lot of the work you're going to hear about today. So I want to cut to the chase because I think I like to cut to the chase and then I'll backfill it in. There's no doubt that plastics are a pollutant. Amazingly, almost everything that you hear in the news or read about or the public perception is often not particularly accurate. And if you try to trace back what you've heard, there's really no source. It's almost startling when you start to look and you try to trace back when somebody says you eat as much as a credit card of plastic, credit card's worth of plastic every year. And you follow where that came from, and it just came from an environmental group that had no data to support that. Somehow or another, they thought that it was a good phrase, and in reality it is. It's, you can envision it. It's actually very clever, but it's not substantiated in science. It can be very confusing. Of every pollutant that I've ever studied in my career, hands down, plastics will be the hardest I will ever study. There is nothing even remotely as close in terms of studying my world of types of chemicals I think about than plastics. For many years, I think the type of science and what we needed to attack this problem was a little bit behind, but it's catching up in full steam. And I think it's going to take at least a decade or even more for us to be even in a position where we can actually have some comfort and confidence about what is going on with plastics in the environment. We're a long way. That's not to say that it's bad news. It's just it's going to take time. So you can't go a day without hearing about plastics in the environment. And I think I was standing outside for 5 minutes and I saw the video screens about straws and other aspects. So it's in our lives. We hear about plastics time and time again. It's, in some respects, it sometimes drowns out climate change and other potential environmental stressors, which is frustrating to a lot of scientists. And in other cases, folks are very happy to hear that something is getting elevated into the public when it's a potential stressor. So it's in our lives. We read about it every day. We see it every day. There's a large movement there. I want to first talk about getting into the idea about why I said plastics are so hard to study. The problem is when you study something like a pesticide, it's just one single entity. It's one. So if I had I could draw it in like 3 dimensions. I could show you and I could say, this is the pesticide. And I own that structure. I know it. Plastics, every piece of plastic in the environment is like a snowflake. None of them are the same. We face an incredibly daunting challenge about trying to constrain what is out in the environment. So you can have, these are called nurdles, and up here, that's the raw material. So if you make plastics and you're selling it to somebody else who wants to make it into a bottle or straws or even something like a medical device, they actually come in nurdles in different colors. Of course, you can go and filter out toothpaste, and those are plastic abrasives. These are what we call secondary plastics. These are kind of the pieces that you typically see in the ocean. They're pieces of plastic that came from somewhere, but you can't trace back their identity. They're just part of this group. And then you can have these microbeads, which have been banned. And those are the microbeads that you might have seen in facial scrubs and other detergents and personal care products. And then across the spectrum, you're going from very, very small to something like these fishing nets, which are ghost fishing. They call them ghost fishing nets, which are there's a lot out there, and it's a considerable concern for large mammals and fish in particular. And then you can go to beaches. This is the beach off of Australia. And, I want to drive home this concept of difficult. Every one of these pieces of plastic probably has had a little bit different life beforehand, and the way it might have been sitting on the beach, whether or not how much sunlight it was in it, or what was the drink or the material that was inside it, or how it might have been handled by the original owner or the secondary owner. The point of the matter is that each one of these pieces of plastics has a different story. And what the next chapter in this book, we don't know from here where this piece of the plastics go. But I want to underscore to you, it is a very difficult problem when people say plastics and you say, what type of plastic? What size? What color? And then also there's additives that are added to the plastics to make them more pliable, to make a reaction go faster, to change the color. Many, many additives are added, of course, that also change their behavior. And then on top of the colors and the shapes, we have different formulations. So if you recycle and you have to look upside down and you see the numbering system, the recycling numbering, you'll see that there's typically 1 through 6. Some towns might not accept 5, and other places might accept others. But you have polypropylene, the low and high density polyethylene, and these squiggly lines represent approximately the density of the ocean, the seawater. So if you're above, if you have a density less than water, seawater, you would be you most likely polypropylene and the polyethylenes, and then polystyrene, which often we think about as foam, is also also has a solid, and it's also in compact disc cases, which to us is like 8-track tapes for other folks in the audience. You guys don't remember CD cases that much, but the point of the matter is actually polystyrene's right here. It's pretty close. Typically, we don't see much PVC, and then the big unknown, or the unusual plastic is what we call PET. And PET has a density of 1.4. So it's about 40% more dense than all these other plastics, including polystyrene. That means that for all things considered equal, the plastic that's usually in most of the drinking bottles and soda bottles is PET. In theory, that should sink. So colors, shapes, uses, previous history, who owned it, where it was. Each one of these different plastics has a different chemical structure. They're all polymers. And on top of that, they have different densities. So somebody says, I'm worried about plastics. Not to sound like a jerk, I would say, which one? And that's kind of annoying, but it's that difficult of a problem. And, one of the things that we're trying to do, and a lot of folks are trying to do in research, is maybe make the point that it's very difficult to phase out every type of plastic. And we're going to get back to that. But can we recognize the ones that may have the longest lifetime in the environment, the ones that may potentially have the greatest harm? And so maybe we can start to reevaluate how we produce some of these products in a way that we can avoid the ones that are the biggest challenge and not so challenge. So it may be very difficult to constrain and understand plastics as a big whole. But that doesn't mean that we can't take strategic bites in certain places to make a bad thing from getting worse. It's interesting. One of the first research papers on plastics in the environment was actually done by a previous colleague in a building that I have. Sometimes I use as I have some office space in there, and I actually didn't even know that until recently. Well, I guess in 2010 or so. The point of the matter is that this is two colleagues at the same institution I'm at wrote a paper. They were off the coast of the United States in what they call the Sargasso Sea. When they were out there looking, actually more interested in, so I'm not a biologist, so to me, you're either a bug or a big fish or whale. It's easy that way. So they were out looking for bugs and towing nets. And when they towed the nets and they came up and they wanted to count critters, they kept seeing pieces of plastic. That was in 1972. And there were several other papers published in 72, 73. Some colleagues out in the Pacific Ocean were doing a research cruise, and they ended up starting to notice so much plastic and junk in one area that the scientists, being scientists, decided to keep track of it. And they wrote and they made a junk log, and that was in 73. So by the early 70s, it was pretty clear, and these were papers published. Science is one of the top tier scientific journals in the world. These papers were published. They were well known, well received in 72 or 73, 74. So it was aware that plastics was out there. And in some of these papers, they were actually we're starting to worry about whether or not that they could act as sponges for PCBs as a chemical, and actually that they could capture PCBs, and then the plastics would even be more toxic. They were way ahead of the curve because they predicted it and actually came out as true. So the point of the matter is that there was some really sound science in 1972. And I actually would argue that if I could get away with it without getting my degree taken away, I could resubmit this paper today. And it's so relevant and so well done, it could get published as new research. So even though it was in 1972, they did such a good job, it's a very tight paper. Now, more recently, I've been working with colleagues about looking where plastics are in the environment, and this is a heat map, which where the heat map of the northwestern Atlantic Ocean, and this is the United States eastern seaboard, and the warmer colors are where the amount of plastics is high, and the cooler colors is where plastics are low. And this is kind of a smooth data set from many trawls of a net. So they would be on a research vessel, they throw a net over the side, they tow it at a certain amount of speed for 1 nautical mile, they bring it back up on the deck, and they count the pieces of plastic. This is the end result of many pieces of plastic that have been picked by all students who are undergraduates, who pay to go to a place called Sea Education Association, which happens to be in Woodsall as well. What I want to drive home to you is that plastics in the ocean, when you look at even this one figure, are not uniformly distributed. That we don't see all yellow or all red or actually all blue. It seems to be that there's some areas where they're higher than others. The other thing for me, having studied a lot of pollutants, is typically the amount of pollutant is highest near the coastline. And as you get away from the ocean, get away from land into the ocean, its abundance drops. In this case, you get into the middle of the ocean, and it gets increased. So, we have a really hard problem of materials that are being released into the environment. We have some idea where they're going, but they seem to behave in a way that certainly shows something going on in the environment that does not let them to be equally mixed. Right? There's not an equal distribution of plastics in the surface ocean. And this would be about the top 3 feet or 1 meter. And all this data came from undergraduates who do 6 weeks of land course at Sea Education semester, and then they go 6 weeks at sea on a sailing boat research vessel. The students deploy this net, and then they actually handpick what's on the net and catalog it. And this data set is the most robust and detailed data set on plastics in the history. And it's all been generated by conscientious, hardworking undergraduates. Again, I want to drive home to you that you as potential scientists, or whatever you do, you can make a meaningful and important contribution. And so many of these students led to that figure. This is one of the most well-known figures in plastic science, and the only thing I did was help pick what colors it was, in some respects, in kind of a relative basis. The point of the matter is that we know where plastics are. It's on the backs of some really fantastic, many students who had to go and do that. And what that woman on the right-hand side was doing was she was picking out pieces of plastic. So a typical net tow was actually yielding this type of material. And you can get a feeling that it's hard for you to identify what that plastic was initially. You can certainly, this is fishing line. That we couldn't figure out. The rest of it, you can look at it a little bit more detailed and find out what polymer it was, whether it's polystyrene or polyethylene, but just visually, you can't really pinpoint where they're coming from. You can see some of these ones that have a much more defined shape. These are those nurdles. Those are the ones that's how the plastic company delivers a raw material. And you can see the penny there is for size. That's what's collected on that net for 1 mile in the top 3 feet. This is a map that was generated about 2 or 3 years ago. And this is the sum of all the data that we have about plastics in the environment and the surface ocean. The ocean makes up 70% of the Earth's surface. I would say, in my world, we would say that this is a particularly lean data set. That there are expanses of the whole Indian Ocean, much of the Southern Pacific Ocean, Western Pacific. There's almost no data. This is an incredibly huge amount of the ocean that's been undersampled. And quite frankly, these symbols are actually kind of skewing the concept that even these circles are actually too big. They should be much smaller in terms of what they represent as a sampling effort. So each one of these circles represents a toe or maybe 1 or 2 toes. So again, when I talk about things like how much plastic we would eat, and when folks say there's more plastics in the environment than fish, it's difficult for us to test some of those statements when we have a relatively patchy amount of data. We do have a lot of data off the coast of the United States where I just showed you. We also have a lot of data off in what we call the Eastern Pacific, Northeastern Pacific, off the coast of California. You can see where in the kind of that orange zone. That orange zone is what's typically called the Great Pacific Garbage Patch, which drives every scientist who studies plastics absolutely crazy. The scientist who actually made up he was pressed. This was in the 1990s. He was an oceanographer, and he was pressed by a journalist who said, "Can you give me a phrase that kind of describes what's out there and what's there?" And he just said, "Oh, it's kind of like a garbage patch." It isn't a garbage patch in what you think of. It's not this vast surface of plastics like you see like that beach. And in fact, I've never sailed through it, but I've seen a little video. I have a lot of colleagues. When you do sail through what they call the garbage patch, and they make statements about how large it is in relative to Texas, there's plastics there. But you don't see much more by your eye. You only see that when you tow a net and you get more up on the surface. I'm not discounting the potential input. I'm just trying to underscore the fact that when you think of garbage patch, you should just think about the fact that the nets have more plastic. It's not like you're walking across a dump. Nevertheless, there's a reason why there are areas that have more plastic than others. I don't have that much time to go into that, but it's the way which the ocean is not like the water in your bathtub. It has the way the winds blow around and the way in which the earth tilts and is affected by the moon and its gravity. you have these areas where the ocean circulation moves. And when it does this, it creates what we call a gyre. And the gyre acts like a big lasso or a rodeo, and actually can encircle. And once you get caught inside it, it's hard to escape. And we call these convergence zones. There's 7 of them in the world. They happen to be that when the plastic might float, if it gets entrained into that circle, it's now being concentrated in the amount of plastics. So the more plastics that get released into the environment, where it is unlikely for us to see them in a lot of places. With time, as it gets a chance, if they continue to float, they will be concentrated in certain areas. Now that's unfortunate in some respects, but it's fortunate in another way that if the technology came along in a way in which you could meaningfully clean up the ocean of plastics in a way that was sustainable and safe, you at least don't have to go everywhere. You can target these areas that we know from the physics of the ocean surface that they can strain and rodeo them. So that's relatively really good news if you're always trying to be on the positive side. The interesting thing is, let's go back. Really good papers were coming out here. This is the history of production of plastics. Let's just pay attention to the blue. This is the amount of plastics of all those polymers produced in the U.S. Nope, in the world. No, U.S., sorry. So really good papers here. Typically when people give plastics talks, they want to talk about this movie called The Graduate. I'm not going to do that. You guys can go and watch it if you want. The Graduate was right here. So the interesting thing about this movie is we were in a time in the 60s where there was a great awareness that DDT, which was a pesticide that had great skills and powers to kill pests and saved a lot of lives, but also was very tough. When I think about tough, I think about the fact that Mother Nature couldn't beat it up. And when you looked at its structure, you could understand why DDT could persist so long. And then in the mid-60s, scientists started to identify PCBs. You're going to hear a really great lecture by a really good scientist in a few weeks on PCBs, so you're in for a treat. But awareness on PCBs was around here, and it became very quick when scientists started to see where they were and how they were built. So, kind of visualizing these molecules in three-dimensional space, they could say, oh, I can see why they last this long. They have this type of way, this kind of force field of skills that they don't get beat up by nature. And if somebody stopped and said, okay, we're making a lot of plastics, and somebody stopped and looked at plastics, they would say, we're going to have a problem. And the data was there. For whatever reason, it wasn't capitalized. The reason why in this movie the young graduate was told to get into plastics was because it was a big industry, because it had great potential, that it was going to be where the money is. And the movie was right, because there was a lot of potential in the production of plastics. Plastics are the 8th largest industry in the United States. They are used in every possible way in our lives. And you could argue that the awareness and the flag of concern for plastics in the environment was in the early 70s. And then the scientists who did a really good job about explaining that there was a problem with plastics in the open ocean, and the one scientist who coined the phrase garbage patch was in the mid-90s. So around here. And those folks and other colleagues did a really nice job of explaining the science, where this plastic was, the amount that it was there, at a level that it was well communicated and accepted that we had a plastics problem, that there was plastics in the environment, and it was of concern. And now, up into 2010, we've seen major efforts to reduce the usage overall, great awareness, many different types of bans, folks making a sincere effort to try to get less pollutant into the environment, and yet production continues to increase. It's kind of startling that something we hear about as something bad for the environment it's hard for folks to say, and they keep getting more and more every year. Well, it's a big industry. It employs one way or the other somewhere around 1 million people at the first start. And a lot of different plastic products actually are very fruitful and useful to humans. A lot of medical devices. There are places where a plastic is actually the best product you could have. Makes our cars lighter. There are very positive outcomes of having these materials. But on the flip side, they're being used in a manner that is non-ideal. And so there's this push-pull about our need and our usage. And I would challenge any of us to try to go plastic-free for a day. It's much harder than skipping a straw. If you think about where plastic is in our lives every day, every moment, I have to give up this pointer just to start off with. It's extremely challenging. My point here to take this home is that the idea that we're ever going to outright ban plastics is not going to happen for a long time. It's just too ingrained in society's needs for that to happen. That doesn't mean that we can't pivot and do a better job in trying to reduce the amount that gets released or create greater awareness or reformulate some of these materials so they ultimately have a less impact. But this is a daunting challenge that is faced about plastics. Just to drive this home even harder, this is why it's so hard. You have all these other polymers, so all these possible polymers. Then they add flame retardants, fillers. You guys are all good folk. Top of a Starbucks coffee lid is only about 85% plastic. 50% of it is non-plastic material added as a filler. Because it's cheaper and other reasons. And then they're used in everything. They can have a variety of different sizes. They can be made into small fibers, strings, foams, films, pellets, and they can be a wide range of colors. So trying to get an understanding on every different possibility is going to be hard. That doesn't mean we can't target. We be strategic. So I'm giving this lecture in 3 parts. This is the first part. Depending on how well I do, we might go into part 3. Hopefully we learned a little bit about the plastic's a problem, but there are big knowledge gaps. The ocean's been undersampled. The average depth of the ocean is about 15,000 feet, 5,000 meters. All that data I showed you of the whole ocean, that was only the top meter. So that's 1 over 5,000. The bottom of the seafloor has sediment or mud. Very few samples have been taken from the bottom of the seafloor. So trying to constrain or trying to balance our budget about how much is coming in, like when we try to balance our cash and money in our lives, is not balanced. We know we've made a lot. We know we can find it in certain places. We don't know where other pieces of plastic are. And so we have yet to balance and have a comprehensive understanding of where it's made, where it's released, how it behaves, and how it ends up eventually, where it eventually exists or it doesn't exist. And I want to really take home that despite all the great awareness and efforts to reduce a pollutant, it still continues to get made more and more. And it will be very difficult for complete replacement. So my colleague and I, Colin Ward, we were working on a project, that's part 3, about how fast sunlight might break down plastics. So we had some of our original data. We wanted to go back and see what had been done throughout kind of the scientific history in the last 30 or 40 years about what other scientists have determined how long and how fast a particular plastic product could break down. So we went on this great effort to try to find out all the data we could. In fact, we asked another undergraduate, this part of this work hasn't been published, another undergraduate to go and look for every piece of plastic data that ever existed. And she created this massive spreadsheet. And ultimately, we found out that there were about 42 of those like infographics you might see at the beach or at a museum or other places that kind of give you some insight about how long different pieces of plastic last in the environment. And of those 42, within them there was about 158, something might last for 10 years or forever. Different languages, 5 different countries, 3 different languages. We were kind of blown away when we started to go through this data. And this is one of these types of figures. This is a figure, it's going to scroll through. This is so I'm going to show you 57, and we went through and looked at every one of these. We kept track of all the different, how long they all last. I have to give these folks credit. Some of these figures are really well done. The graphics are nice. Some of them are really clean and clear. Others, they're fine. The point of the matter is that there's a lot of posters and infographics out there about how long a piece of plastic may last in the environment. I'm going to try to focus in on 2 numbers. We're going to talk about how long a plastic bag is going to last in the environment and fishing line. So we went through all these data and even nappy, which of course is a diaper. So there's you can see these different languages here. The other thing that's kind of noticeable is sometimes the data is really tight. Like somebody's giving a number with really great confidence. Some of them give ranges, which is a little bit more reasonable. And like I said, these graphics are really well done. Some of them have an overprint from solid sources, or British BBC is very well done in terms of that. So so Colin and I went and looked at all the data for plastic bottles, 6-pack rings, plastic bags from groceries, disposable diapers, styrofoam cups, and plastic straws. This gray bar is the range and reported lifetimes for these products. So, and the average, which is kind of arbitrary, was about 400 years for soda bottles, but anywhere from 100 to forever. Plastic bags, we had the smallest number, I think, was one year, and it went all the way up to forever. I'm going to go back to plastic bag, and I also want to go back to fishing line up there. Most of the numbers were 600. It was kind of surprising to us that every time we saw a fishing line, it was 600. How is it possible that there's so many data points, and must have been on the backs of different scientists, and they all got 600? It almost seems too good. When we went through all this data, and we tracked it all back, and in fact we contacted a lot of the folks who made these graphics, none of this data came from a scientific study. There's no data to support any one of these values. It was kind of startling to us that we actually kept asking. We kept asking, you sure? We didn't. And then, as we did a little bit more reporting, we ended up finding out that actually most of these numbers, about 100 of those 157 numbers that you would have taken home from that, going through that film, came from 3 different posters. So 3 posters actually were the original source for most of this data. How other pieces got in there, we don't know. But I think I can't remember how many fishing lines of 600 years. I'm going to get back to fishing line for 600 years. Every time, 600. It came back from 1 poster. And that just kept being the source. This is the problem. This is a problem this is not me trying to bash well-intended folks about how to communicate a problem to the environment. This is a problem because, good science helps make good policy decisions. It helps inform consumers about what they want to buy and not buy, and ideally also informs industry about what they may want and not want to produce. And when you see stamps from scientific institutions in well-respected areas of values that could be up to forever, and then others are saying 1 year, it weakens our knowledge and our understanding. And, that's not ideal. So, this can be frustrating, but at the same time, it is a really good argument about why we should continue to study plastics, because at this current point, it's a wide unknown. And so I'm just going to show you a couple of these. So this is the one, actually, ironically, that was made to a government office that's about maybe, I don't know, a tenth of a mile away from my office. And this is the most used figure, I believe. And I want to just remind you on the fishing line, 600 years. We got plastic grocery bags, about 20 years. Some of them had different things besides plastics. This is the source of many of the data points. So now Nantucket is an island not too far away from where I live. It's an island, depends on how far you get there, but it's I think about 40, 50 miles away if you have to take a ferry or fly there. And Nantucket's figure has plastic bags up to 500 years. So two different government agencies about 50 miles apart. And so we have plastic bags 500 years, and the other one's 1 to 20 years. There's big differences, and yet none of them can be sourced back to a real, true blue scientific study. Let's go back to fishing line. We consistently saw fishing line at 600 years. And then we saw fishing hooks. You know what happened? One of the previous figures had fishing line and then a hook added to it to show what that fishing line was. It was associated with fishing. The group that made this figure misinterpreted the previous graphic and put 600 years on a piece of metal and not the fishing line. Showing this to you folks here as undergraduates who are asked to write term papers and do your due diligence when you're doing your research, and don't use Wikipedia. Question your sources. Ask if that data is accurate. Good scientists are even better skeptics. And this is an important point, that these figures, I think, were done admirably. Their intentions were good. The graphics, some of them are fantastic. Some of them aren't so great. Depends on how you like graphics. But the range is too big. And it shows a sense of a lack of knowledge. And that can be problematic when you're trying to make policy decisions and trying to inform the public. Okay, so this is part 2. How am I doing on time? I can't see the reflection. Okay, good. So, information varies. Big differences. You could argue it's poorly done. And again, when you go write your term papers and your papers for class, this is a classic example of when you make a photocopy of a photocopy and you make a copy of somebody else's statement, don't make a fishing hook. This doesn't have to do with plastics. This has to do with due diligence. And but on the flip side, you can say, look, the goal of one good science project would be we want to make the best poster. We want to make the most accurate poster. And it might have big error bars. It might be a big wide range, but at least it's grounded in science. The reason why we got into these posters was we kind of started to think about, everybody kept saying plastics last forever in the environment. And I would argue that microbes, especially for most plastics in the environment, do not break down plastics. Microbes should, every year, win the Nobel Prize for chemistry and biology and arguably physics. Fantastic capacity to do chemistry, biology, ultimate in terms of their capacity to do amazing things. But plastic stymies them. And that's interesting that nature can't break down plastics, at least in an appreciable manner. Sunlight has never been really looked at very closely, which kind of surprised Colin and I when we started to get into it. Colin and I were looking at photochemistry, how sunlight broke down oil. And Colin was working with me, and he had a really strong background in how sun reacts with materials. And so we grew together and worked as a team. And so we said, let's figure out how fast plastics break them down. it's not a stretch to do that. But, coming home again, this is what we kept seeing, that plastics always seem to last for a long, long, long time. There's no data to say that. And most of the time, the reason why it was pointed that they lasted for a long time was that microbes couldn't break that down. And at the same point, we can't balance the books about where is all the plastic that we've made, how much we made to where it is. So you could argue that it's just because we haven't found it with sampling, going out in the field and making those poor undergraduates pick those pieces of plastic out. But is some of the plastic not there because it's gone? Did sunlight make it go away? And that was kind of the question that Colin and I had. This is not surprising. The reason why this t-shirt or your clothes sometimes fade and die, especially from sunlight, is because the dye or the material that was added to make that shirt green reacted with sunlight and faded. So that is, right here, that is photochemistry. Or this beautiful red shiny paint job. That is fading. That is a chemical reaction that has occurred that has affected the red pigment that made that car red. It's been attacked by sunlight. Let's go a little bit closer to what's important in our everyday lives. We're going to talk about liquids, and this is a study. We would call it organic matter. Let's just call it a tea. This is Lipton tea in another tea bag, brewed tea, put out in the sun, plain old sun, like your backyard. You come back 100 days later, and you can start to see that sunlight has a great capacity to change the color and, in theory, other aspects of materials, the small compounds and other compounds that make up tea. Tea is also a very complex mixture. It's not just one tiny molecule. It's many of them. And interesting also, notice that these are both tea, just one happens to be light and one happens to be dark. And one is more reactive than the other, or susceptible to sunlight than the other. Now, I'm a big Diet Coke fan. Diet Coke really gets beat up by sunlight. Look how fast. They got taken down in 10 days. And then the other thing I'm a big fan of is coffee. And it hung in there pretty good. So these are two different types of organic materials that when exposed to sunlight, and we did controls and all that, reacting and being more susceptible than others. This makes total sense. You sit down, you look at the reactions, you look at the molecules that are going to be attacked, and it makes sense. And we also can see it with plastics. When you see plastics that have been out and exposed to sunlight, they fade. You also see that when plastics are out in the sun too long, they become brittle. Brittle's a big concern because when a piece of plastic is brittle, it can break into smaller pieces and potentially smaller pieces. And if they get so small, we may not be able to detect them, and we may actually be eating them. And when they get really small, they can potentially affect human health. That's not been really worked out yet, but it's a good working hypothesis. What we did, Anna, this is a grad student, who's working with Colin and I. We bought 5 films of polystyrene from manufacturers, 100% right at the beginning, hasn't been added any color. They're all clear. And we did some experiments with sunlight equivalents in the lab, but it's very representative of true blue sunlight. 5 different plastics, all the same material, roughly all the same thickness. You couldn't tell them apart if you looked at them. And when you expose them to sunlight, we found out 2 things. Sometimes you could see some plastic actually going all in that in some experiments, the plastic would get, the sunlight would act on it and actually literally turn all the plastic into carbon dioxide. It was startling to us. And more often than not, we would see that the plastics first got broken down a little so that it was no longer a solid material it was kind of dissolved. So you couldn't see it physically by eye, but if you looked at it with other means, you could still see that there was the skeleton of the plastic there. And if you reacted it with more sunlight, it eventually would get driven to carbon dioxide. This is a big deal, because that means that, in theory, in the environment, and we're starting to see this with field samples as well, that plastics can actually go into thin air. That a piece of plastic actually can react in the sun and get taken down by sunlight, or broken down enough that it's no longer this solid material. We don't know whether or not how toxic and how problematic this in-between skeleton is. Now, this sounds like great news, and it is good news in some respects, because it points to the fact that nature does have a capacity to take down plastic. What's surprising to us is that of those 5 plastics that were exactly the same by eye, and when we bought it from the manufacturers, this is how much CO2 was produced from one of our experiments. So don't worry too much about the units. And these are the error bars associated with these experiments. 5 plastics, all look the same. Couldn't tell any difference from them. When you do these sunlight reactions, this Fisher one was much more likely to get converted completely to carbon dioxide than this one over here. That's good news that it gets broken down. It gets even better news when you start asking why. Because if you start asking why, then you can start to say, well, what makes this so interesting? What skills does this plastic have, or its weakness, in some cases, to sunlight, that it's getting converted all the way into carbon dioxide disproportionately than the others? That's a great opportunity, because we could take this knowledge here and drill down as to what makes these different plastics different, and then communicate that back to industry, which we're doing, to help design better and safer plastics when we need to use them. And another really strong piece of data for these experiments is the more light that you exposed, the more material that you made. And this is also a control. So if it gets covered and it doesn't get any sunlight, that's what's getting made. So this is just some data that we're showing. But let's not go out and celebrate. For these reactions to occur, it's still going to take 10 years or so, maybe 20 years for this polystyrene. That means it's not a free pass to throw out polystyrene films out the window. It means it takes a long time. Even when folks say, well, I'm using this biodegradable plastic, it's not a free pass for a variety of reasons. But let's even assume it does get biodegraded, but it takes 10 years. That's 10 years that piece of plastic may make a bird choke. So how we formulate things is good news. We can change that. But it's not necessarily mean that a new formulation is not a free pass. It might make things a little bit better. But it's not a perfect fit. And we have the same outcome for the dissolved materials. Getting into that dissolve phase is a lot faster. I just want to finish up here. Sunlight can break plastic down, but it varies. What we found out, and I didn't have a chance to get into it, is that when you drill down into those 5 plastics, some of them had some additives in them. When you look at what the additives were, they were types of materials that would have a capacity, for lack of a better word, to catch that sunlight and concentrate it and allow it to be even more reactive. And it made sense, which always makes you feel good when you're a scientist, when you see some observations and you can actually explain them once you investigate even more deeper. So these are really exciting for us. And, we're working very hard in close contact with some industry who are keen to understand what is the Achilles heel of certain products. And so how can we make future materials that will be at least less harmful? But it's not a free pass. So I'm going to go back to our takeaway. I think they're definitely a recognized pollutant. We don't have the data yet to even get a handle on how harmful they are, triaging them in the grand scale of all the potential stresses that we have in the environment. We don't have that data yet. It's very confusing because they're really hard to study. I do think the awareness to the scientific community was a little lagging. There's a lot of good science going on, a lot of good research questions going on, and I think that's going to drive the field to a point where we're going to have a much better understanding of where are the areas that we should be most concerned about and where are the areas that we shouldn't be as concerned about. I do think it's going to take a long time. And that's somewhat frustrating, but at the same time, you know, you have to deal with what you deal. So I'm going to end by saying that this college is a state-funded public institution. And I think they're the jewels of society and education. And I say that because I'm a product of almost a mirror image school in Rhode Island that you have here. And the education I got was fantastic. And I suspect you got the same one. So I like to show when I give talks, every school I went to, all funded by the Rhode Island government. I am a product of all public schools. I am proud of it, and I think I'm as well prepared as any other schools, and I'm not dismissing any of them. The point is that for a while I left and I was, you know, in these different academic strata, and you would feel bad that you went to a state school. And then when you think about the small class size, the intimate relationships you have, that the teachers know your name, and they want to help you, and they're committed to this community, you find out that it's an incredibly great deal. And we're all lucky to have that. It's unfortunate that light isn't shined up on it enough, no pun intended, tonight's talk. But either way, Chester Barrels, Edgewood Highlands, Parkview, Cranston East, Rhode Island College, University of Rhode Island. State schools are great, just like this one. So I'll take any questions you have, and happy to have you here.